for, okay, recording, okay.
Sure.
And thank you everyone for attending this seminar today. So I'm going to talk a little bit about the work that I've been doing since I was starting my postdoc and continue as a faculty now. So basically this work is on multi-skill modeling of structures and materials. It's considering the computing aspect, data science aspect, uncertain aspect. And I have to start to apologize that I was planning to talk about goal engine optimization, but then I figured that maybe I won't have the time. So in this talk, I will just limit that part and I will focus on the first three topics. All right. So I'd like to start with description of how a general mechanical engineer will work, right? So normally a mechanical engineer, when it's trying to design something, we will be given an application, be it to design a bridge frame or design a car body or whatsoever. We will start by thinking about what is the potential material that we can use to achieve our goals, right? So, we will start with a class of material or space of materials that can achieve our goals. For example, we can think of metals, or we can think of composites, depends on the end applications that we might be interested in. And we'll then need to think a little bit about the structure of the or the topology of the design, right? So which approximate structure of the topology can satisfy our requirement, right? And given this tool, we will then use the thing called constitutive model to basically link our materials and our structures. And with this, we can then start to basically really to design, and by saying design, what is really speaking is basically optimization process to basically optimize for the performance and cost. So that is basically minimization procedure. And that is basically how a general flow of the work of mechanical design. And this, of course, we're all very familiar with this constitutive model. It depends on what material we're looking at. This constitutive model can change, and it can be either plastic or elastic or viscoelastic whatsoever. There's tons or millions of constitutive models out there. But if you ask this question, so where does this constitutive model comes from? And this actually, this constitutive model actually can come from direct experiments. We have standard experimental procedures to basically calibrate our constitutive models. It's basically, you can use DIC, DVC these days, which are really advanced experimental techniques, or you can just use a good old tensile test, might also do the work. And so this is one way, or another way of this, where this constitutive model can come from, is it can come from low-length scale model, right? So for example, if we're thinking of metals, then a suitable low-length scale model in the polycrystalline level would be a crystal plasticity model, right? So it described how the still continuum, but it describes the deformation of in the grain level, right? And of course, if we ask where does this low-length scale model comes from, it's again, it comes from low-length scale experiments, right? So here I'm showing you, this image of the microstructure of a metal composites, all alloys basically with precipitate. And if you ask, again, we can play the same game. So if we ask where does this low-length scale model comes from, it comes from an even low-length scale model, right? It's for example, we can go one step down and then we enter the regime of molecular dynamics. And if we go to one further step down, we're going to quantum mechanics. We're going to first principle, where ideally we would not need any experiments, and we can just do everything from scratch. All right. So this is basically, a general sort of framework for multi-scale mechanical designs. Basically, we can track down the scales and really go into lower and lower length scales to a point that we really do not need any experiments, as well as we can incorporate more and more length scale features through this kind of framework. So my talk today is going to be focusing on this framework and trying to answer three aspects of or three questions arise from this framework. So the first one is, it is great that we have and all these lower length scale models, we have investigated enormous amount of resources and time to study these, but nevertheless, it is this kind of in a practical mechanical design, people it's really rare that we will use all this knowledge directly in design. It is nowadays mostly it's indirect. Basically, knowledges. It's directly using the lower single models and integrated with a practical mechanical design remains something that is still unachieved. And my first talk is basically, and the reason is because these lower single scale models are really hard to solve them. They're really time consuming. And the first talk is going to focus on, can we accelerate the solutions of these lower length scale models? And I will explain in detail what I mean by this in a second. Now, the second part of my talk is, now suppose we have all these models at each length scales working, high fidelity models working very well. How are we going to basically bridge the scales? And how can we do it efficiently and fast? So that, by the end of the day, we can achieve this goal, that we can really have some hope that we can use this, lower length scale physics to inform directly in our mechanical design, right? And then the third talk I'm going to discuss today is, remember, in all this process, there will be uncertainties everywhere. In each length scale, there's a possibility that one can, bring up uncertainty either, from it can be uncertainty of the models, it can be uncertainty of experiments. So how should we quantify this uncertainties? Specifically for this Multiskill framework. All right, so that, and then I will stop and conclude. So let's start with the first topic, which is how this is focused on how we can accelerate the solution. So as I said, the dream of computational solid mechanics is basically we seek to reduce the number of experiments we need as much as possible by replacing with the experiments with these high fidelity numerical models. However, these numerical models, especially in lower length scales, is extremely expensive to solve. And just to give you an example, so for the three-dimensional polynomial design cluster, it takes 1 to 2 days of computing time in more the HPC, right? And if you go to one scale lower, if you want to solve dislocation dynamics, discrete dislocation dynamics, it can take up 1 to 2 months to even finish one single calculations for a single grain. So this is, you require enormous time to basically solve these fully resolved PDEs. And the question we ask is, can data science help? The answer is yes. But before I answer that, I would like to just step back and have a reflection. So what do we mean by saying all these lower length scale models? So all these lower length scale models actually can be unified by partial differential equations, which most of all of it is well known. For example, in the continuum level, we have the classical continuum mechanics, and that is basically a wave equation in the dynamics and elliptical PDE in static. And for example, for the phase field, then we're trying to model the evolution of the interface, and that most of the time can be considered as a diffusion type of equation, right? So we assume that there is the first order dynamics for interface. And of course, for the MD, it's when we really get down to the bottom layer, things gets more difficult. And for the MD, it's essentially we're not sometimes dealing with stochastic differential equations. So basically, we're putting some Gaussian noise into our Gaussian random variables into our PDEs, and that requires special consideration. But nevertheless, the message I'm trying to show here is that all these low length scale models can be unified by partial differential equations. And the question really to ask is, can we accelerate the solution speed of PDEs? And that is going to be the focus of the next few slides. So, we're of course very familiar. This is well known how to solve a PDE. This has been, we know this since when we have finite element method since 50, 70s, I think 60, 70 years ago, right? So, what a classical way or conventional approach of solving a PDE is. So suppose we were given an initial boundary value problem. I'm not going to describe the details, but given this, this is basically a classical continuum mechanics governing equation. And to solve this problem, so what we do is we basically use an approximation. We discretize the solution and approximate using either polynomials. If I approximate the solution U using polynomials, this is finite element method. If I use a neural network to approximate the solution, this is going to become. Oh, my apologies. So this should be what I meant here is this is an N, not a polynomial interpolation. But nevertheless, if I use a neural network, this is something called physics-informed neural network. But again, this is basically in the framework of solving a PDE. And so after we have this approximation, we'll basically plug this in a weak form of this PDE and it will solve user system. It's basically usually in form of linear equations or linear ODEs. And so this is the standard procedure, basically. And of course, also here I correct. So this is again, this is a neural network, not a polynomial interpolation. So of course, the good thing about this is, this is very general. Although that if we change our materials, for example, the parameterization in this closure constitutive model, we will need to resolve this or rerun our solver, go through from 1 to 3 again, or when we change our loading or boundary conditions, we will need to resolve this again. The one drawback of this is that this solution is really mesh dependent, meaning that our error or the error you get of the solution of this using this class convention approach is going to depend on how well you discretize the spatial and temporal domain. And also to be able to solve a PDE like this, we would need to know explicit physics, meaning that every the governing PDE for the for the constitutive model has to be explicit known, as well as this balance conservation laws. So these has to be explicitly known for us to basically solve that in this manner. So we need to know physics. So another alternative approach is this data-driven approach. It's basically what we're trying to do is we're trying to learn a PDE. And what we mean by learning PDEs is we consider the solution of a PDE as an operator or a map side dagger. It's basically a mapping between two function spaces. E would be the input space of quantity of interest. It can be the coefficients or the materials, or it can be the boundary or initial conditions. So this, or it can be both. So this E is basically input function space of quantity of interest. And this U is, of course, our output space of QI. It's not, usually it's displacement, but that doesn't need to be that. It can be strain, it can be strain, can be stress whatsoever. So now we're given a set of data, Cn and Un, where this Cn is taken from V, and according to some probability measure mu, and we will have our corresponding solution Un is basically side dagger of Cn. So this is our data. And by learning a PD, what we're really trying to do is we're trying to identify a parameter space theta and operator class psi, so that the psi parameterized by the theta can approximate this side dagger. Now, in other words, what I'm really meaning here is that we're going to basically collect a distribution of data, not one PD, but a distribution of them, and according to some probability measure. And I'm going to basically approximate this side dagger using this a neural network or neural operator. I'm going to describe immediately. And of course, the drawback of this is it requires training data, but nevertheless, with this kind of approach, we do not require 100% explicit norm physics. All right, so the physics can be hidden, but all we need is this input-output data. All right, so but this idea seems to be very intuitive. Why haven't we done this 20 or 30 years ago? Now the reason is because at that time, we really do not have the computational or the tools or the numerical tools, which is this neural network, which is we have found it surprisingly expressive. And let's take a step back and look at what exactly is a neural network and why it is so it has so much expressivity. So the mathematical structure of a neural network is really simple, and I'm sure a lot of us you would be very familiar with it. So classical neural network architecture is basically it's trying to approximate a finite dimensional maps from V to U. So V lives in RP and U lives in RQ. And what a neural network does, so suppose we were given a vector V, we will first do a linear affine transformation of V, parameterized by some unknown parameter Aij and Bj. All right, so this is the first thing a neural network would do. And then it will add a local nonlinearity, I call it sigma. And it can be, or the machine learning people will call it activation functions, can be, either sigmoid, ReLU, there's quite a few of them. And afterwards, so this linear and this global linear and the local nonlinearity will basically compose one layer of neural network. And the so-called deep learning or deep neural network is basically you keep composing this global and the local operation again and again and again, so that you increase the depth of your neural network. And the so-called training or learning is basically a minimization task where we seek to minimize the loss, which is the neural network loss function, which is the neural network output, compared with the truth, which is the UI star, this is the data. And we're trying to minimize this against our parameterization A and B, right? So this is a very brief description of what a neural network does. So surprisingly, this simple composition architecture really has a strong expressivity, and what people has been finding is that this kind of composition architecture is very good at approximating nonlinear maps and nonlinear operators. And if you think about it, this is quite remarkable, because prior to this type of composition architecture, for example, if you think of FEM, we're really familiar with architectures which add things together, not compose things together, right? So it seems like doing composition really expand expressivity a lot in the compared to just do a expansion or Taylor's expansion style of approximation. So the question we ask is, okay, so this is a classical architecture. Can we extend this idea based on the how a conventional neural network would look like? The answer is yes. So what we call neural operators is a direct extension of a conventional neural network. So the key idea here is that we observe that in a conventional neural network, we will first pass our input to a global linear affine transformation. So this is just, so suppose my output of a layer, temporal output of layer Z is after the global linear affine transformation is basically Aij Vj plus Bj. So this is very simple. So what we have been trying to do is we're trying to expand into a more general case. So rather than doing this matrix multiplication, what we can do is that we can replace this simple matrix multiplication by an integral transform, all right, with some kernel ki parameterized by theta. So the benefit of doing this is that now you can see that this kernel, the integral transform, is mesh independent because I can evaluate this. If I can learn this ki theta, I can evaluate it anywhere in my domain, and I can do this integral. And also, it is possible for us to impose some structure on this ki theta rather than letting it be totally random and learn from data. We can basically impose certain structures to it. For example, if you impose in a discrete way a filter or 3x3 matrix, you say this ki theta is a sparse matrix. Or it's just a filter, then you recover the CNN, the convolutional neural network architecture. But of course, this expression is more general. And this is the key idea behind neural operators. So this is where we're trying to basically generalize this global linear affine transformation in a conventional neural network to this integral transform. And of course, there are different integral transforms that we can use and different kernel architecture we can use. So we have basically come up with a few of them. This includes graph neural operator. So you can prove that graph neural networks is basically a discretized version of graph neural operator. And we have multiple graph neural operator, low rank neural operator, and Fourier neural operator. So among all of this, what we find the most successful one is this Fourier neural operator for solving PDEs, and I'm going to focus on this architecture in the next couple of slides. So what a Fourier neural operator does is we'll basically, so giving an input V, we will first do a pseudo-structural Fourier projection of this V using this F operator to project this into some Fourier basis. And then we will learn this kernel basic convolutional integral operator or kernel ki theta through data. So and that basically forms the top layer, this Fourier transform layer. And of course, only doing this is not enough because Fourier transformation only works for periodic functions. To basically rescue us from only being able to dealing with periodic functions, we'll now add a conventional affine transformation with Wi and bi to basically, this is basically would really help us to extend this to functions or problems functions which are not periodic. And so this would compose one Fourier layer. And again, what I want to emphasize is this is nothing but a expand of the idea of linear affine transformation to integral transformations. And then you just basically compose these Fourier layers again and again, and you use this P and Q. These are basically project operators or encoder and decoders to basically pointwise project this your input to a higher dimensional space, and you do basically learning things from there. The reason of that is basically because there's a nice theorem from Koopman saying that in infinite dimensional space, everything is linear. And that's why all of us are firmly believers of expanding neural networks into high dimension. It really helps. So, all right, so this is the architecture of the Fourier neural operator, and I'm not going to go into too much of details, but showing you with some of the results. So here I'm showing you a case study of 2D Navier-Stokes equations. So what you're seeing here is basically evolution of vorticity. So you can see that, so these are basically the evolution of vorticities. These are the ground truth solution given by the numerical solvers. These are the neural operator predictions, and you can see that they correspond to each other, agree with each other pretty well. And what is also quite impressive is that using this Fourier neural operator, we can really speed up our solution. So this thing is approximately 1,000 times faster than traditional solvers. And also, when we compare this Fourier neural operator architecture to all the other neural network architectures that we find in literature or we define ourselves, we can see that this FNO really outperforms for all the other architectures. For the testing case that we're showing, this is Burger equation, this Darcy flows basically. And an additional good thing about doing supervised learning function space is that we can really achieve the so-called zero shot super resolution, meaning that because we're learning a kernel, which is resolution independent. So what we can achieve is we can train our neural network at 256, and then we can test it at all other different solutions. And in these two cases, this is exactly how the study is done. So we train our neural operator at a low resolution, and we'll test it as a high resolution. And you can see that using this, neural operators, that everything, and with NO is neural operator. You can see that this arrow remains a constant, meaning that we gain this resolution independency without the need of really showing neural network that at this high resolution. And you can see, of course, a conventional fully connected neural network doesn't have this. And obviously, when you increase the resolution, train here, train your architecture at this resolution, and you increase it, you see that your relative error increases as well, right? So this is the benefit of using this design numerical method in function spaces. And okay, so this is what we have for now for these neural operators. And the second topic I want to discuss is, all right, so now we have a relatively satisfying surrogate models for solving PDEs. How are we going to bridge the skills between the different length scales? So what information should we pass basically? So and if we think really about this, is a question about a dimension reduction, right? So when we really moving from a low length scale model to a high length scale model, do we really need to pass all the information that we have on a low length scale, or is it sufficient that we only pass some of it, or a part of it? And that basically involves the increased, crazy dimension reduction procedure. And the answer to this is that it's the mathematical theory of homogenization. And the answer is yes. So we don't really need to pass all the fully resolved micromechanical details from a low length scale model to a high length scale model. And there are two basically mainstream ways to deal with this problem. So one is this so-called sequential multiscale modeling, where we're basically saying that the low length scale model and the high length scale model are linked by a constituent relation, which has assumption where we say that our macroscopic quantity of interest, for example, the stress, can be fully captured by the average of the microscopic strand physical variables plus some hidden state variables. So this is basically the fundamental assumption of thermodynamics, right? So we're saying that we really don't need the theoretically infinite dimensional information from Rowland scale, but we can reduce it to some finite dimensional state variables which capture the state or the memory of the material. And of course, we would need to basically subspecify the evolution, how these state variables would evolve. And this, of course, requires, first of all, the identification of internal state variables. And it requires a priori postulate of the evolution of these state variables, right? So here, for example, in most, if not all, these homogenization procedures, we will assume that there exists some first order evolution dynamics for the state variables CT. And this can be fast, but of course, there's no way to justify that whether this assumption is true or not, right? Whether it can be that you identify more than enough state variables, or it can be the case that you need infinite number of state variables to fully describe this. We don't know this, right? So this is the drawback of sequential multiscale modeling. And another way is called concurrent multiscale modeling. So rather than postulate a functional form of the constitutive models, concurrent multiscale modeling does is at every macroscopic spatial point x and time t, we're going to pass the strand, for example, as a boundary condition to the microscale problem, and we're going to solve this in the cell problem, the fully resolved PDE, and then we compute the microscale stress everywhere, and then we basically pass it back to the microscale problem, right? And you can imagine that this is immediately prohibitively expensive because I need to do this for every spatial point x and every time t. So, and especially when we have history dependency, doing this would mean that for every time step, I have to not only pass the stress at time t, but also pass all the stress strand at time t, but also all the strand histories in order to solve this single cell problem. And I need to do this for every point x. So this is, quickly becomes intractable for practical problems. And normally, in most cases, we won't even be able to fit this into our computer memory. So, but of course, the benefit of this is that we do not need a priori postulate on the functional form of that. We just solve this microscale problem and just bypass the spatial average stress into the microscale problem. So what we are proposing for this learning-based multiscale modeling is rather than actually solve this lower landscape, fully resolved PDE, which is very expensive. Let's just replace that with a neural network or neural operator that we have developed. And what we seek to achieve here is we seek to replace the expensive unit cell calculations with an inexpensive deep learning-based surrogate model. We're asking this question: so can we achieve concurrent multiscale modeling at the cost of constitutive updates from a data-driven approach? So the answer is yes. And actually, to achieve this, we here use another architecture called PCA-NAT. The reason we're using this not for operators is because in this case, the computational time is even more critical, and we're really trying to achieve reduced dimension reduction models, or reduced dimension surrogate models to achieve fast computation speed. So the architecture of this PCA-NAT is the following. So given our input, x and output y, we will first project these two functions into a reduced subspace, reduced dimensional subspace RD1 and RD2. So this D1 and D2 is normally significantly smaller than the discretization of X and Y given the data. And this is achieved by the so-called encoder and decoder architecture. And for this, you can use either PCA or autoencoder, and there are a range of them that one can use. But in this study, we use PCAs, and hence we call it PCA net. And after this dimension reduction process, we will have reduced dimension X and Y, and then we will basically build a neural network between these reduced dimensional spaces. And there is a very nice theorem proved by Kowalski, actually. He is a postdoc, he is a PhD student at Caltech, stating that so if you use this architecture, we can guarantee that, suppose we have enough data and we have enough reduced dimensional, reduced dimension D1, D2, we can prove that this architecture can approximate, pretty much all the psi is of practical interest, so that we have an error which is controllable and can tends to 0 if we have infinite number of data, or we include infinite number of dimensions. So with this, we test this idea against something called crystal plasticity. So this is a popular model for polycrystalline solids, metals, grain level. So the Downey equation I've listed here, it's a bit complicated, but nevertheless, the important thing to remember here is that in the micro scale, we have 4 groups of state variables which are critical. So one is this grain orientation. So we have, in this unicell problem, we have a bunch of grains, each of them have different orientations. And we have associated with it, we have the plastic strands of each point in the cell FP. This is another state variable, and we have the plastic deformation, which is characterized by the slip system, slip systems in S, slip systems, and we have also included twinning there. So we have this anti-twin systems where with this lambda beta denoting the volume of twin volume, basically. And so with this, so as you can imagine, to solve this system of PDEs in a micro scale is very time consuming. So what we have tried to do is exactly to basically replace this expensive solution procedure using this PCA net. And we're trying to basically, our goal is to find the mapping or the operator which maps the macroscopic strain trajectory E of t defined on a fixed time interval 0t to the macroscopic stress trajectory sigma of t defined again on a macroscopic interval 0 to t. And of course, we can do this. So what we have done is we generate data, and then we train this. And I'm going to basically skip a little bit about details, but impress you with the results. So what I'm showing you here is a comparison of neural network prediction, which is the dotted line, and the true solution of our numerical solver. And you can see that the both neural network solution and the numerical solver agrees with each other pretty well. And what is really remarkable that we found during this exercise is that the neural network really has enormous generalization power. So in this study, we have only trained our neural network with random functions. By saying that, I mean that we have put in the space of our strain input and strain input to using a Gaussian measure. So you can see all our input training data would have the feature of randomly increasing and decreasing trajectories. However, after training this, when we test it against mechanical relevant loading passes, for example, this is a uniaxial tension test, this is loading on loading, and this is cavity expansion. None of them has this random increase and decrease in feature, but nevertheless, the neural network works. The PCA-net is able to generalize to these kind of mechanical deterministic functions or deterministic logic passes pretty well. And what we have noticed that it doesn't work in the other way around. So if you train it with a determinist function, test it with a general function, this normally doesn't work. And one of the current studies we're doing is we're really trying to understand what is the best probability measure that we should impose on our training data so that we get maximum generalization capacity. And of course, an additional benefit of doing this function-based learning is, again, you can achieve a zero short sweep resolution. So we train our neural network in a fixed resolution of 200, and afterwards we change it. You can either increase or decrease the resolution. It's okay, you get the same test error. And so the other thing which is quite impressive that we found through this exercise is that we can really learn physics from data. For example, in this study, we didn't show, we know that all our physical models are causal, meaning that the solution, the stress, for example, at time t would only depend on the past of the stress strain history, not on the future, right? So this is the requirement of thermodynamics. And we don't impose this in our neural network architecture. We just, feed to the neural network a fixed time interval. Nonetheless, when we test it, we have found that the neural network is capable of, capturing this causal feature of our model. And this is an example to show that. So here we have a bunch of stress strain trajectories which converges before a branching time TB and diverges after it. And you can see that immediately afterwards, both the neural network and the true solution diverges after this when t is greater than TB, right? And then this is a similar proof where we basically random stop our uniaxial tension test, and you can see that neural network. So this dotted line is neural network prediction. You can see that it relaxes immediately when we stop our test. And similarly, what we have also found is that we can discover isotropy from data. Again, we're not in this. So here we're training a neural network with data generated from a random texture in microscale, meaning that we don't have a preferred texture of polycrystals. And you can see that we know that we would expect that this, the microscopic response of this material would be isotropic. And when we test our trained neural network by rotating the uniaxial loading axis, we see that the stress strain curve is approximately a constant. So that is basically a sign that we can capture isotropy, although that we don't impose this in our architecture. So now we will have this this model learned. We really try to basically use this model in a true multiscale manner. So here, what I'm showing you is a FE square style calculation where each material point has this trained neural network as a surrogate model, rather than bypass this to a unit cell problem. And I'm showing you an example of plate impact test where we have a rigid projectile hitting a plate at time 0. And here, and this is how the our neural network or learning-based multiscale model predicts how this plate will deform. And so, of course, what we have found is that this using this kind of learning-based multiscale modeling, we can really enormously increase the speed. So if we compare this with conventional FE square, this is 10 to the power 6 faster. If you compare this with a Taylor average, it's 10 to the power 3 faster. And if you compare this with a conventional consider model, then we are only about 10 times slower. So this, using this learning-based circuit model really can increase the computational speed. So, and that concludes the second part of my talk. And the third part of my talk, and I know that my time is limited, I will try to go through this relatively quickly, is the multi-skill uncertainty quantification. So we know that in all these procedures, we will have uncertainties associated with different length scales. And the question to ask is, how do we quantify the propagation of uncertainty through the length scales? So for example, the question really to ask, so suppose I have uncertainty at this very low length scale 6, how would this uncertainty propagate by the end of the day to my application, the microscopic application, right? So now the challenge here is that if we don't have this hierarchical multi-skill modeling structure, then this becomes a task impossible, because that means that we will need to run an integral test, which includes all the microscopic details up to this 6. And first of all, it is impossible most of the time to run a calculation or a test which has this integral feature. And so that's the really the motivation of this multi-skill uncertainty quantification task. So what we're trying to really achieve is can we basically find a way to avoid doing this integral test, basically by doing a really gigantic calculation to include all the low-length scale features? Can we basically smartly break it to pieces where we don't, mathematically speaking, we don't want to basically evaluating the composition map of different length scales? Can we basically find the rigorous bound of this composed map, so that we eliminate the need of this integral test? And the answer is yes. The theoretical tool that we've used is the thing called modeling of continuity, and it is actually turned out to be a natural quantification of subsystem uncertainty. So I will not basically go into the details of what is a model of continuity, but rather simply put in, a model of continuity is basically allows us to basically break a composition map. So if I have some uncertainty basically with the input of Fn, so rather than evaluate this Fm composed with Fn, I can use basically I can first compute Fn associated with uncertainty. Basically, we compute the model of continuity associated with Fn and use this as an input when we compute the model of continuity of associated with Fm. And mathematically, you can rigorously show that if we decompose this Fm and Fn using this model of continuity approach, this would be a rigorous upper bound, meaning that the value of this model of uncertainty associated with Fm composed of Fn is always going to be smaller than this bricked model of continuity using this subsystem uncertainty formula Kj. And this really allows us to basically break this integral test to a bunch of subsystem uncertainties, which we can easily evaluate at subscale. And I'm going to basically show you an example. So here what we have is a plate impact of magnesium alloys, where we're trying to quantify the uncertainty which is associated with the slip of the and twin critical resolved shear stress, which is a grand level uncertainty. And we're asking the question, how would this uncertainty propagate all the way to the microscopic ballistic performance? And we've basically followed this model of continuity approach, and what we found is that by doing this evaluating the subsystem uncertainty, what we can evaluate it is that suppose now I have in the mesoscale we have this such uncertainties. We can really first compute model of continuity from for this microscale. We can compute from micro to meso the Multiscale would basically compose of this kind of Johnson-Cook parameters, A, B, and C. And then we can basically then pass this meso to macro, and then combine them, we can get a micro to macro uncertainty, basically. So this graph shows how the microscale uncertainties would affect the backface deflection of the plate. And also it shows how each uncertainties on each slip or twin systems would contribute to the total backface deflection. And so that is basically the power of this model of uncertainty approach, where you can really break down, the subsystem contribution to the total uncertainty in the macro scale. All right, and this brings me the summary of today's talk. So what we really, found is that there emerged a general framework for multi-scale material and structure by design. And within this framework, we've looked at, circuit modeling to basically speed up low-length scale models. And specifically, we have proposed these Fourier neural operators for fast PD solution. And we'll also look at how can we efficiently bridge in between the scales. And to this end, we have proposed this learning-based small scale modeling. It's called PCANet. And the third question is, how can one quantify the uncertainty throughout length scales? And to this end, we have basically used idea of model of continuity and proposed this hierarchical uncertainty quantification approach, where we can really quantify the microscale uncertainties and how it propagates to the macro scale. And with this, I'm going to end my talk now. So these are all the references I used for this talk. And thank you again for your attention, and welcome any questions. All right.
Right. Thank you, Dr. Liu, for the awesome talk. Fantastic. Now it's the floor is open for questions. Does anybody please feel free to comment either on the chat box or just raise your hand so I can start asking questions. Anyone?
Yeah, Jin? I think Jin raised hand. I think.
Oh, okay, Jin, go ahead.
Yeah, thanks, Liu Qi. Thanks for this very exciting talk. My first question is so you mentioned the pin at the very beginning of your talk. Mm-hmm. So I may miss some information. So comparing the pin and your method, the Fourier neural operator.
Yes.
So do you have some comments or guide? So what time or what situation we should use which, or your method is always better than pin?
No, okay, that's a great question. So pin, where's what happened? So pin and neural operator works on very different scenarios. In pin, you don't need data. So pin is, you can think of pin as a alternative to FEM. So really speaking, what pin does is we're not going to use this polynomial approximation for in the FEM. So right, so we're not going to use that. Let's use a neural network. So that's all what pin does. So in that regards, if you use pin, you don't need physics. You don't need data. But the cost is you have to know full physics, meaning that we have just like to solve a FEM problem, we have to know what is the governing equations, what are the constituent models, and we're basically using exactly the same trick to solve it, solve it using pin, right? So we all this solution procedure is basically similar to what one would use in FEM. Rather, you just use the pin, and you can naively just use a gradient descent method to minimize the PDE loss, and that's what pin does. Or there's some recent work where you can design scalar pin and all this by basically combine everything what pin proposed into what everything the FEM people has done for the past 30 years. I mean, nevertheless, this pin is a very powerful tool, and of course, people working on pin, all this physics informed neural, we have physics informed neural operator stuff. So the claim is that we would be able to completely replace that with FEM. I have personal doubt on that, but nevertheless, that is the claim that people are making now. So, but this kind of thing is very different from a neural network or data-driven approach. So here we need data. Of course, it's a drawback, and we need basically general training data, a lot of them. But the good thing is that we don't need explicitly known physics. So partly known physics or even fully unknown physics is fine, as long as we have enough data which embodies the true physics inside it. We can nevertheless use it to learn the physics. And this, I've shown that here in this learning-based multi-skill model works that you can actually learn physics from data using this data-driven method. Now, of course, one appealing direction is you can fuse these two things together, right? You can have partially known data, partially known physics and partially known data, and that is basically you just add a Lagrangian multiplier or penalty on a loss function, and you can easily achieve that. So, but to answer the question, yes, they are trying to answer the same question from a completely different angle, and each of them have its own pros and cons.
I see. Do you plan to share the methods you used at some open source codes to the community?
Yeah, it is already there. I can, after this talk, I can. Yeah.
Oh, thank you. Yeah, that's my question.
Okay, so I saw another person, Teng. You can go ahead. Teng, I think you can go ahead and ask questions as I raise your hand already. Yeah. Oh, sorry. First time, doing this thing. How do I unmute? Jane, can you help me out?
Yes, I will help.
Okay.
Okay. Yeah. Thank you. Yeah, very nice talk. I think this is also my first time to use this. I cannot unmute myself. Looks like the host should unmute. So maybe some setting has been changed. Okay. Yeah, I think that's a very interesting talk. Thanks a lot. I have a relative technical question. I don't expect a very detailed answer, but I want to ask you, very high level. I noticed for your second part, you already upload your code on the GitHub. I just so had a very brief look, and that's a VU mat. And I want to ask the general pipeline for this setup. And you call this Python script through your VU mat, this like a Fortran code. Is that right or not?
No. So yeah, I mean, you can basically compile a Python object and compile the Python to be a executable file and call using Fortran. But what we have done is here is we basically explicitly coded the neural network in Fortran for the VU mat. The reason is because it's faster, and Fortran is an old language. So so really why we're going to this hassle is because we're trying to use Abacus, and Abacus forces us to use Fortran. And machine learning is done using GPU in Python. So in theory, you can basically just call Python from Fortran, but that includes a lot of I/O operation that makes things slow. So what we have done by the end of the day is just write the neural network architecture in Fortran. And I think the code that I've shared on GitHub has that coded Fortran, has the Fortran code, which has already have the neural network architecture coded there. So if you're interested, I can send you email, explain all this, but
okay, sure. Then I think your Python code is for training. Then you identify the network parameter you input to your Fortune. Is that it?
Yes.
Okay. Yeah. Thank you.
Thank you.
Okay, I have another one. I have a question. Ask. Should I click the ask to unmute one, or how does that work more?
Hi, can you hear me?
Hi, yes.
Thank you for this very nice talk. I have a small question about the plate impacting plate property you presented like in the middle of the presentation.
Yes, 1 second. Yeah, this one, okay.
Yeah, perfect. So my question is, I think this is not a quite typical finite element problem because there involves quite a lot of nonlinearities like geometrical boundary conditions. So how do you deal with such problem? Because you don't use like much about the physical details information. So,
yeah, good question. So the detail of nonlinearity and all that is embedded in the training process. So we have, for example, in training, we generate data using these random functions, and all the geometric nonlinearities and the time dependency, path dependency, and all the nonlinear stress-strain behavior are basically embedded in this training data. When we basically train this neural network using the solution of unicell nonlinear problem. So that's how we basically been able to include all the material nonlinearities in this problem. Now, talking about geometric nonlinearities, it's basically we use a general framework where we bypass deformation gradient. And again, in our data, we have this microscopic Cauchy stress. We can use PR focus, but we use this Cauchy stress instead. That's how basically we embedded the geometric and material nonlinearities in our model by basically by basically learning from the data.
Okay. Thank you very much.
Thank you.
Jin, go ahead.
Yeah, Liu, I have a question just following Han. So Dr. Liu, so you mentioned here for the plate impact, so I can imagine it can be a high strength problem, some ballistic regime. So for your solver, are you solving the viscoelastic problem, or you just solve there's no history, no viscoelastic those effects?
No, that's we are not in the shock regime. So there's history dependency. And in our microscopic model, we're not assumed we're in that shock regime, so that the strain rate is not as far as what Suraj will do in his experiment. So we don't have that viscoelasticity, but we do have viscoplasticity.
I see.
So that's where the memory comes from. So I mean, we can of course include viscoelasticity, by saying that imposing in the grand scale, if we have the microscale physics, which end up with in the microscale end up to be what we call viscoelasticity, that we can also include. But nevertheless, we don't know 100% how would we include viscoelasticity. What is the micromechanical source of viscoelasticity in the macroscale? In that case, I think that's still a debatable question. I don't know. I think so, but nevertheless, we don't consider that in this problem. But path dependency is there, definitely.
Okay, so you mentioned in your viscoplasticity, you use the path dependency. So when you train your model with those data, do you plug in lots of this data because you need all the history of data? Is that correct?
Yeah, definitely. So basically, it's we're passing in functions, trajectories into the model.
Yeah, thank you.
Thank you.
Yupeng, go ahead.
Hi, Dr. Liu. Very good talk. So I have a few experience with Bayesian method on anthropic quantification, and I'm not quite familiar with your way. So can you explain the difference and the pros and cons about those things?
Yeah, thank you. That's a great question. So Bayesian method basically assumes that we need a probability distribution or probability measure for Bayesians, right? So it's we would assume that our uncertainty follows some sort of form of Gaussian for Bayesian, and or some we need some form of probability measure. So and we're basically trying to infer the probability measure using the Bayesian thing. So what we proposed in this framework here is that we say that we actually don't know the probability measure. What we're really trying to quantify is the bound of the uncertainty, not the probability of the uncertainty. Meaning that we're trying to find the least upper bound of the uncertainty that can be caused from this that caused from this low length scale uncertainties. What is the in the macro scale? What is the bound of the variation of our performance, rather than asking what is the probability distribution of our uncertainties? And of course, that's the key difference. So in this study, we're trying to say that we don't really know what is distribution of the source uncertainty and what is distribution of the end of day uncertainty. Rather, we're just trying to find bound, and that's the key difference. And of course, the pros is that I guess the cons is that we don't really, the information that we can provide using this method is limited, because I will only be able to tell you bounds. And I'll be honest that I don't know if it's least upper bound or not, but at least it's a bound. It won't be larger than that bound. But again, but the pros is that it is assumption free, right? So we don't need to assume that our source uncertainty is a Gaussian, which normally Bayesian would assume that.
Thank you. Very clear. A follow-up question is that, for example, if we have some outliers, then that we may have not that accurate bound compared with sort of a standard deviation or whatever thing come from the statistical aspect. Do you have any comment, any way to avoid this?
Yeah, but I think that's a it's a Bayesian school. People say everything is about belief, right? So if there's outliers, they'll just not believe that it's true. I mean, so for us is for engineering designs, we consider about safety factors, right? If we
to be conservative.
Yeah, to be conservative. Yes.
Okay. Thank you. Another small question is that follow up with your impact test. It's a flat punch of your plate. So I noticed that you have a round angle. That it's not a rigid angle. That did you do this on purpose to because actually this is a classical sleep field theory. Yeah. That the sleep light theory in Hill's in really Hill's book. But you round the angle, make it softer so that it will cost less numerical.
I don't like infinities. I don't like singularities. That's right. And in real life, there's no rectangles exists.
So I'm curious about have you compared this with the analytical solution, or if there is singularity, how will your method? Of course, your method is extremely powerful. I saw that, but do you have any comment? Thank you.
Yes. I think that's the thing that we're currently doing. Just trying to I think you're asking exactly the great question. So whether how would this compare to another solution? And we validated our model in the micro scale. We have done a ton of them just to verify. So this is the cavity expansion and all that. But we have done this for this particular punch indentation problem. And I think so we do see that asymptotic field at the tip. Even if you have a round angle, you will still have asymptotic field. But although it's not going to infinity as elastic solution would be. But again, I want to draw attention that this is not pure elastic calculation, it's elastic plastic. So with hardening and all that, so that complicated things.
Right. So actually, this raises the last question is that it really matters the quality or say how accurate you can get from your data is extremely, like basically you have to have a significant variety of your database training set. Then you can maybe predict this, because this is much more complicated than what you have trained for. So
definitely, yes. So first of all, the data has to be relatively, error-free. If you have any errors that's in the data, is okay. If we have some controls on that, so there's again a branch of field. A lot of people are working on that field. So how to denoise the data? It is possible. You can use autoencoder to do that. If you have, some truth, data, truth. But nevertheless, part of data should have this ground truth embedded in it. It's okay that if you have other data which doesn't have which have some uncertainty inside it, but you will then be able to decompose the uncertainties with the truth. But nevertheless, that is something that we need to have. But again, I agree with you. I mean, the data has to be relatively clean. Thank you very much.
More clear. Thank you.
Thank you.
Okay, given that I think we're almost past our time, so let me probably ask one last question, if I may. So I noticed that you mentioned that when you talk the second part of the talk, you mentioned about a different surrogate model, the PCA net, compared to the first one, which is the Fourier neural operator. So you mentioned about the speed, but I'm just curious, could you comment on why the reason you end up using different neural nets for the second part of the talk? Because if you solve a Fourier problem over a periodic boundary condition, it's pretty fast, right? So that's sort of kind of like has the advantage if you're doing FE squared. I'd say if you choose a RVE, you solve the problem. So I'm just sort of like curious, what's the reason you changed a different circuit model for that?
Yeah, well, I guess Fourier neural operator, it's a great question. We should have tested that in this learning-based problem. Now, the reason for intuitively that we don't choose Fourier neural operator is because in this problem, we want to do dimension reduced order modeling. So this RD1 is much smaller in the input dimension X. So this is encoded. So we are basically doing dimension reduction in this process. While in the Fourier neural operator, in order for us to have enough expressivity, this P is a lifting operator, where we are going to pointwise lifting this to a very high dimension. So this is what convolution neural network does. CNN. So if you I don't know if you're familiar with that, but what CNN does is at each point I'm going to first lift our input to so-called channels, and that is nothing but just lifting the dimension of the input space. This Fourier neural operator is great in the sense that we achieve really minimal errors and in a relatively satisfying speed. But because of this lifting procedure and just to trade the expressivity, we really lift this into a very high dimensional space. In contrast to this PCA net, where we compress this into a very low dimensional space. So that is basically why we choose this PCA net, just for the sake of speed.
Oh, I see. So over here, when you do the order reduction, do you use a PCA? Is that principal component analysis that you have reduce the dimension of that?
Yeah.
I see. So the X is sort of the input you can get from all the FE Gaussian node, is that you get the data. I see. Also, in that case, I'd say if you use a different mesh, right, and you get different number of Gaussian point, then the PCA will give you probably a different dimension of the data. Is that something?
That's the thing is, yes. So you can, the key thing here is we're going to project to the same PCA basis. So so the data resolution can change. It can change whatever they want. But nevertheless, we're going to project it to the same PCA basis. There's a way to do that. You can fix the PCA basis. And by doing so, you can achieve resolution independency basically by saying that I only need to train a neural network here. And all the encoding and decoding process can be dependent on PCA. And but you don't need to retrain your network.
I see. So I guess let's say if you have a denser mesh, what you can do is like some sort of interpolation, so they can fix the base of the PCA.
Yeah, sort of that, and then you can just use the same. You can use the same neural network for that.
I see. Thank you, Dr. Liu.
Thank you. Yeah.
All right, Jen, you want to take over and do some concluding remarks, like saying about what's going to happen next week, things like that.
Oh, Liu, I don't have those. Just please follow our Twitter, WeChat accounts. So we'll post an advertisement before the next week event.
Okay, all right, yeah. Thank you everybody for coming to today's seminar. And with that, I guess probably thank you, Dr. Liu, again for giving this wonderful talk. We look forward to see many of you next week on Sunday.
Bye.
Bye.
Bye-bye.
Good weekend.